My name is Michael Dexter, and I'll be talking to you about magnesium alloys and their application in additive manufacturing and comparing their properties as additively manufactured components to wrought and cast. Traditionally, you see magnesium as being die cast because it has some really good die cast properties. So the one far on the left is actually traditionally manufactured, but it's a biodissolvable stent. Very small, as you can see by that size scale. It fully dissolves into the body, which is really cool. And then that's pure magnesium. So magnesium is the lightest of all the structural metals. It has the strength to weight ratio comparable to high strength steel alloys and high strength aluminum alloys, but it's a third the weight of aluminum, it's half the weight of titanium, and it's much lighter, 75% lighter than steel. So it's been used, the image off to the bottom left is again a bioabsorbable, biodissolvable clip that they're using in medical applications. Um, GM is actually working on magnesium sheet metal in cars because it has a higher specific stiffness. So it has a higher flexure modulus, I guess, than aluminum and others. So it resists denting, things like that, better for its weight. So it can reduce the weight of vehicles and make them more fuel efficient. And high performance cars have been using magnesium engine blocks, cast engine blocks, and wheels for quite some time. Um, so they have good corrosion resistance. Many are heat treatable. They have lower specific heat than aluminum, which is good because it lowers the melting cost. Aluminum is fairly expensive to work with to melt as far as energy goes, and it has a much better machinability and higher fluidity, which means you can do things like casting better. I didn't see per se how that affects additive manufacturing, but I would assume that flowability of the melt pool positively impacts additive manufacturing. So here's some common alloys, and a few of these alloys have been investigated with additive manufacturing. I really like their naming convention because it's easy to see what they're alloyed with. Off to the right is kind of the convention. Anything with A is aluminum, anything with Z is zinc, etc. And then the numbers represent percentages. So it makes it kind of easier to know what an alloy actually is and why it has some of the properties. So you can see some of them have higher corrosion resistance, some of them have higher strength. AZ91 B and D were investigated, and also AZ31 B were investigated in the research studies. So here's some additional properties that I was able to find. There's actually some that are tungsten uh, alloys, so they have a small percentage of tungsten in them, which gives them some very unique properties, as well as neodymium, things like that. So you can see some of the ultimate tensile strengths over there. I believe that it's in MPa, so 30 to 40 MPa, which is actually very beneficial for medical applications because that lines up very nicely with natural bone, with its properties. So you can see again dent resistance, machinability, specific strength, weight, um, etc. All those properties compared to other metals is very good. So a couple of the vendors that I was able to find: ESM, SMT. They produce AZ91. A lot of these are in mesh size, so I don't know if they're gas atomized. They're mostly spherical powder. They're not super small. They're about 44 micron. And then this magnesium electron powders, they make several varieties. A8, which is mostly magnesium with a small amount of aluminum, AZ31, AZ91, and WE43, as well as their proprietary Electron 21, which has a high neodymium content. So I wasn't able to find any specific case studies on research about its applications for additive manufacturing. So the first study that I was able to find was this effective energy input on formability, microstructure, and mechanical properties of selective laser melted AZ91D magnesium alloy, published in the Material Science and Engineering Journal. So they were looking at a variety of laser processing parameters, and specifically energy density, joules per cubic millimeter, and how that affected things like density, hardness, strength, corrosion resistance, microstructure, etc. And they did that by looking at single tracks, and they also did that by making these tensile bars. And that's an image of the nice spherical AZ91D that they were able to find. Um, so this is a chart of how the energy density affects. They again did kind of a scanning study with power and speed, as we see in a lot of these additively manufactured, especially with laser centering, to look at, where's the good weldability, what causes balling, what's not enough to cause fusion. And they're able to find good ranges in kind of the middle left section um, as far as scanning speed and things like that. And then they also looked at hatch spacing and its effect with scanning speed on the relative density. So generally you want to keep those fairly high so that you can achieve good mechanical component properties, although there are some applications where controlled porosity is good, especially for biodissolvable, biocompatible things. And this is one of the important things that I was able to take away, is that a fairly high specific energy on SLM parts produced the best UTS and strength at 2%, which I guess that's yield, and then elongation. So, and that's compared to traditionally die-cast AZ91. So you can see that all of the properties as far as strength go are higher, but the elongation is lower. That's because it's a harder material because of higher cooling rates than you can achieve in die casting. So it has a much higher, more eutectic microstructure, which we'll talk more about in this next study. So the microstructure analysis of magnesium alloys melted by laser irradiation. So this one wasn't a powder bed. They actually took cast plates and laser irradiated it and looked at the surface and how it changed the surface properties, and particularly the corrosion resistance, which I found was interesting. And they were able to look at, this is a chart off to the left. I am not 100% familiar with corrosion, but evidently the laser treated is lower, so it has a lower corrosion factor, or is more resistant to corrosion than the untreated, which is on top. And that's the microstructure that they were able to produce. So it has a very fine eutectic alpha beta microstructure, and they found at different laser powers and scanning speeds they were able to actually control the growth of alpha versus beta microstructures. So it kind of opens up the possibility to do layered properties, like for instance, you want a strong core, or maybe a flexible core with a strong outer layer and then a very corrosion resistant surface, that you could theoretically do. Since all these different laser parameters, you could layer the properties really nicely, just by choosing different scanning patterns. So that was kind of an opportunity. They didn't really discuss that, but that's definitely one of the things that's exciting about additive manufacturing, is layered and controlled and engineered properties on a volumetric scale. So they showed that, again, much better corrosion resistance. And these are the references.